Have you ever wondered how to run Java programs on modern hardware like GPUs, FPGAs, etc.? Well, in this video, I will explain to you a solution by using the TornadoVM programming framework. I will explain the TornadoVM programming model in detail, and we will dive into an example. And we will play with different options with the API in order to run on GPUs. So by the end of this tutorial, you have all the key components to start coding your own examples and run on GPUs or any other compatible hardware. Exciting, isn't it? So if you're interested, let's do it. Let's start with a general overview of the TornadoVM software stack and the main components as shown in this figure. At a very high level, TornadoVM exposes an API for Java developers. This API contains the main building blocks to be used by developers to express parallel applications, identify which methods to use and which methods to offload, and finally, how to run applications on GPUs and FPGAs. So this API will be the actual content of this video. Under the hoods, the TornadoVM runtime system and the just-in-time compiler optimize, compile, and dispatch the input application on heterogeneous hardware. We will not go into the details of the runtime system and the JIT compiler in this video. However, in a nutshell, the TornadoVM JIT compiler extends the GraalVM JIT compiler to offload Java code to low-level GPU-friendly or FPGA-friendly code, such as CUDA, OpenCL, or SPV. Then, the TornadoVM runtime takes care of the data migration, data handling, and execution of the application for the target hardware, for example, a target GPU. So, it is a full package solution that is not only used to program, but also to run and optimize a subset of Java programs and to be accelerated on heterogeneous hardware. So, let's focus now on the API level and how developers can start using Tornado to program applications. But before we dive into the actual components of the API, let's think about the following aspects or the following questions. First of all, how do we represent parallelism in a language that was not primarily designed for parallelism and modern hardware like GPUs? Note that there are different types of parallelization. There's for example, data parallelization, tasks parallelization, and pipeline parallelization. Those are the main types. Thus, ideally, we would like an API to express all these types of parallelization in our programs in an easy manner and for a wide, diverse range of hardware, such as GPUs, FPGAs, even RISC-V accelerators, etc. The key word here is representation of parallelization, representation. The second question we ask is, well, let's say that somehow we can represent parallelization. The next question is how we identify the functions or the methods in Java to offload. In our Java programs, usually we have hundreds or thousands of Java classes and hundreds or thousands of Java methods. Which ones should be offloaded? Not everything should be offloaded, of course. There is a target device for each task. So we need a way to identify, the keywords here is identification, of the Java methods to offload. The last question that we ask is, let's say what we can represent parallelization and we can identify, then how do we run it? How do we submit code to the GPU, to the FPGA? How we get results? How we profile applications? The keyword here being run, how to run this code. Well, the TornadoVM API tries to tackle all these questions with different API components. And in this video, the rest of the video, I will discuss each of these components. So let's start with the first one. How do we represent parallelization? There are two ways to express parallelization with TornadoVM, and Java developers can choose one or the other. So the first one is via annotations in the source code. That means that Java developers annotate for loops with the add parallel annotation and reduction parameters with the add reduce annotation for those loops that can be parallelizable. This means that if the loop does not have data dependencies, we can add the add parallel annotation to indicate to the TornadoVM compiler and runtime system that the loops can be parallelizable. So the compiler will apply all compile optimizations needed to transform the loop from sequential to parallel. So in a way, if you're familiarized with OpenMP or OpenACC, in which sequential code is annotated, this is something similar indeed. So you can also annotate nested parallel loops, like 2 parallel loops or 3 parallel loops even. So why is this API? This API is convenient for non-experts on GPUs or FPGAs or non-experts on GPU programming models. Let's say you don't need to understand the GPU programming model in order to use this API. So it's kind of an easy way to get access to hardware acceleration. The second way, or the second API to represent parallelization with TornadoVM is through what we call a kernel API. Developers use this object called kernel context, and this is very low level, similar to OpenCL or CUDA or OneAPI, in which parallelism is explicit. This API is convenient for expert developers that already know OpenCL, OneAPI, CUDA, etc., and want to pour existing kernels into the TornadoVM ecosystem. By using this API, Java developers can access shared memory or local memory, can access barriers on the device, can control the thread dispatcher, etc., of the entire kernel. But in this video, we will focus on the first option, using TornadoVM annotations for loops. Now, going back to our second question about how to define or identify the methods, the Java methods to offload, the TornadoVM API offers a TaskGraph API in which each node in that graph represents a task, a method. Besides, we can add the input and output data to our computation graph. This is useful for the TornadoVM runtime, which needs to transform or perform data migration between the host, the main CPU, and the accelerator, for example, a GPU, an NVIDIA GPU. Since in many cases, the computing system does not share memory for both the accelerators and the CPU. And to answer the last question about how to run, TornadoVM exposes an abstraction called execution plan. It's an object that you can use to launch and enable optimization parameters, enable the profiler, etc., change device, etc. So with that, let's see this in action. Let's go to an example and explain each of these components in more detail. So first of all, let's explore the pure Java solution, no acceleration, and we will start modifying the code in order to use it with Tornado. So what we want to achieve is very simple. We're going to operate on vectors, and we want to do some computation with these vectors. So first of all, we want to initialize a vector, and the initialization could potentially happen on the accelerator. And then we want to compute an operation. In our case, we want to use the math library and compute the sqrt function. So ideally, we want to compute these two functions, as you see in the screen, init and compute square, on the accelerator. In our case, we're going to use an NVIDIA GPU. So the last method is called build and run. It's just to specify the order in which we want to operate. We want first to initialize the array, and second to compute the array with these square values. One thing to notice, though, is that we have a type called float array. This type is provided by the TornadoVM API as well, and it contains, as the name suggests, of course, an array of floating point numbers, FP32 precision. The array is stored off-heap using the Panama Memory API. So the TornadoVM API provides types for 1D, 2D, and 3D arrays, as well as images, volumes, and explicit vector types, for example, float 8. For this tutorial, we're going to stay with the float array, but feel free to scan the whole documentation and collection of the TornadoVM API. I will put a link down below if you want to explore this. The second thing to notice before we jump into the parallel solution is that each of the methods init and copy square returns void. This is on purpose because we already kind of prepared this for Tornado. And the reason, this is an intentional choice, and the reason is that TornadoVM will offload the entire method to run in parallel on the target device, for example, a GPU. Since the target hardware of TornadoVM allows developers to run many threads, usually we're talking about hundreds or thousands of threads, it will be almost impossible to know which threads return a value from an entire method otherwise. This type of limitations is also present on other programming models like CUDA, for example, or OpenCL or OneAPI. So it's not just specific for Tornado. So as soon as we have many threads to run and we want to flow an entire kernel, returning a value as a kernel in the kernel is tricky. So you can have the same approach by passing values by reference, and that's the case of this kernel. Now, let's transform each of the loops to a parallel loop. That's the first step that we need to do. And within each method, we add the add parallel annotation for the for loops. Why we can do that? Because let's look at the first one, for example, the init method. We are initializing the whole array with a value. Each value or each iteration of the loop is totally independent from previous or is totally independent to each other. So that's why this loop can run completely in parallel, and that's why we can add the add parallel annotation in a similar manner to the second method, compute square. So we traverse or we loop for the whole array, get the value, and compute the square root for the value, and we set the result again in the input-output array. Another thing to highlight here in this code is that we transform from math.sqrt, from the math library of Java, to Tornado math.sqrt. So in practice, it's the same function. However, it has some implications in precision. So you can use the Java one, the math.sqrt. However, this library operates on doubles, FP64 values. So be careful because some GPUs don't support FP64. So in many of these models underneath, like CUDA, OpenCL, etc., give you an option to operate of these functions like sqrt, log, etc., with FP32 or even less precision, like FP16. To do that, we can specify with the Tornado math.sqrt, and then we're good to go. So the representation still is in FP32. Let's jump now to the next step, to build a task graph. Remember, task graph is a way to identify the methods and the data to be offloaded. So we create a computational graph, if you like. So to do that, we create an object called TaskGraph, and we give a name. That name is useful if you want to see, for example, the profiler trace, or if you want to change the device, etc., etc. Could be any name. In this case, we put graph. And in between, we have two sets of calls, let's say. One is transfer data, and the other one is task. Let's start with the transfer data. So the first one we see is transfer to device. What does it mean? With this API call, we define all objects that need to be copied to the target accelerator. We also define a mode for each of the objects. In this case, we specify that the array must be transferred every time that the whole graph is executed. So if you execute the whole graph once, it will copy the data anyways. But if you are planning to execute the graph multiple times, you can decide whether you want to copy the data every time or just the first time, so the data is cached somehow. This is important because copying data back and forth across accelerators goes through the PCI Express, and the PCI Express is slower if we take account in the whole overall computing systems, right? So copies are usually slow compared to the actual computation rate. So you can define if you want to copy once or if you want to copy every iteration. In this case, we say every iteration. Another convenient case to specify that we want only to copy in the first iteration is when we have read-only data. So you can specify that with the option of transfer mode first iteration. Let's move on to the second set of calls called task. We can have one or many tasks. In this case, we have two. Each of the tasks point to an existing Java method. Indeed, we can have a lambda expression here. This is just a syntax sugar for a lambda expression. So the task as well, we can have a name, and then we have a reference to an existing Java method. Those methods could be in the same class or could be from different classes, and that's the key. As soon as you have access from this class, the class that creates the task graph, to these methods, you can invoke them. And then you pass the data associated with that method, right? The parameters associated with that method. So we have two tasks in this case, one for initialization, the other one for the actual computation. What will happen though is that when we execute this, I will show you later how we execute this. By default, the Tornado runtime will keep ordering. So if you're first calling the initialization task and the second task is the compute square task, it will keep that ordering. You can influence that ordering, but this is not up to the Tornado runtime. This is up to the developer. Even you can say that different tasks run on different devices. But again, this is up to the developer because you need to be careful with the data dependencies across tasks. As we speak right now, February 2024, this automatic data analysis and data dependence is not implemented. It might be in the future, but for now, just be careful that if you have data dependency across tasks and you want to run on different devices, that's explicit and it's up to the programmer how to do it. The last call is transfer to host. And in a similar manner to transfer to device, this call defines the data objects in which we expect the outputs to be. This could be one or many objects. Additionally, we pass a mode similar to the transfer to device. And usually we want the output to be transferred to the host right after the task is finished. However, in some case, for example, if we have iterative algorithms, we want to execute graph multiple times and only transfer the data at the end of the execution. For that, we can specify that the mode is under demand and is later on in a step when we execute, in which we specify when to copy data. But by default, I think in many cases, it's just in every execution. So we go for this in this case. And we are almost done. We need one more step, and is a way to execute the whole graph. One thing to mention here. When we define the task graph is not executed. It's just a definition of the data that we want and the code that we want to float. But nothing gets executed. It's only through the execution plan how we can execute things or to execute things. How we get execution plan? Well, it's very easy. You build an object called Tornado Execution Plan, and the parameter is an immutable task graph. It's an immutable task graph because task graph by definition can mutate at any point during the execution time, during runtime. You can append new data and you can append new tasks at any point. However, it might happen, if that's the case, it might happen that the GPU is running and you are still appending data and code. That could create a kind of inconsistency in the runtime, in memory, and it could even create crashes. So to avoid this, we can have an immutable task graph. And through that, you are not allowed as a developer to change the graph anymore. You can change the original one, but it doesn't have any effect in the immutable task graph, if that makes sense. So we create an immutable task graph by calling the snapshot method. And once the Tornado execution plan is created, we just call execute and we are done. What happened when we call execute? Well, what happened is that each of the tasks that we specify, the entire method will run on the target accelerator. for example, on the GPU. The rest, which means the logic to dispatch the code, to wait for the results, to send and receive, will run in Java through the TornadoVM runtime. So the TornadoVM runtime is actually a Java process. It's a Java program that just handles and manages the execution on multiple accelerators. With the TornadoVM execution plan, we can do more than just run. Let's look at few examples. So one thing we could do is to enable the profiler. The execution plan API follows the Builder pattern. If you are familiarized with the Builder software pattern, so this API follows that. There are many calls in the style of with action, with something, like with profiler, with device, with warm-up, with etc., etc. I will show you a few examples today, but it's very easy to program and they can even be concatenated. The first that I want to show you is the profiler. We can enable the profiler, and in the profiler as an option, you can specify two things. You can specify either I want to see the profiler live with the console option as we see in the screen, or we can say it's silent and I query the values afterwards. I will show you an example later. Second thing that we can use is to select a device, to change a device. The execution plan gives you an API, a very easy API to query and change devices. This is it's a factory method called getDevice, and there are two values to pass here. It's the driver index and the device index. Driver index is because one driver can have multiple devices attached to it. Let's say an NVIDIA driver can have access to 4 NVIDIA GPUs, and you can access 4 individually if you want to. You just pass the index that corresponds to your system for the NVIDIA driver, could be index 0, index 1. This is up to your operating system and how the TornadoVM sees the devices. And the second is the device index. And once you get the value, you can use the call with device, and you pass the object device, and you call execute. As simple as that. Let's take another example. You can apply warm-up, and this is useful just to pre-compile the kernel. So the warm-up, what we do is to just execute the task graph, but it doesn't run with the data. It just pre-compile the kernels. Compilation is actually fast, depending on the device, but we're talking about a range of 100 milliseconds up to 500 milliseconds, depending on how large are those kernels. And compilation involves two things. It involves Java bytecode down to the target language, for example, Java bytecode to OpenCL, or Java bytecode down to CUDA, PTX, or SPV. And the second step, which is Tornado sends this final intermediate representation, for example, OpenCL, down to the actual binary. These two combined could be, we're talking about the order of 100 milliseconds. If you don't want that overhead in your measurements, you can just say with warm-up, and then the next time you call execute, compilation is done. Another interesting option, and to me this is a killer feature of Tornado, is the dynamic reconfiguration. What this is all about. Let's say in your system you have multiple accelerators. Now the question is, well, if I have multiple accelerators, which one should I offload my code to run? Ideally you want the fastest one, but it depends of what you want to achieve, right? And that's the goal of the dynamic reconfiguration. So instead of rely on the user to try an error on different devices, measure it, and then make a decision, Tornado can do all of it for you. And that's what we call dynamic reconfiguration. So the dynamic reconfiguration, what it does is, depending on an input policy that the user decides, in this case we see it's a performance policy, I will explain in a bit. Depending on an input policy, Tornado will make a decision and will decide which device is best depending on that policy. Now, what the performance policy means is that Tornado will evaluate the execution on all available devices, and it will decide to pick a device based on peak performance. That's the performance policy. Now, how do we evaluate, or how Tornado does the evaluation? That depends on the second parameter, what is called dynamic reconfiguration mode. In this case, it's set to serial. That means that Tornado evaluates first on one GPU, waits until it's finished, then moves to the second GPU, wait until it's finished, then moves to the third device, and so on and so forth. This is useful if you want to have accurate results. Why? Because consider that the multi-core CPU is also an accelerator. We can have a mode, actually Tornado supports it, which is parallel evaluation. What happens is that Tornado will spawn a set of Java threads. Each Java thread is mapped to a core, CPU core, plus it will evaluate also the multi-core system for Tornado as a target device. So depending on the application, you might have like noisy environment, right? To avoid that, you use the serial, but it's up to you what to do. If you don't consider this multi-core as a target, then you can use the parallel mode with no issues. So as you can see, it's very easy, this API. You just call with an action, with profiler, with device, with warm-up, with dynamic configuration. And there are a few others. I will link down below the whole API. And this is constantly evolving, so you might see new calls in future versions of Tornado. So with that, let's jump to an example in the IDE. Let's see the application that we just discussed in action. I will put a link down below for the whole application, so it's easy for you to compile and run and modify as you wish, along to follow this tutorial. So remember, we have two methods, one for initialization, one the other one for the actual computation, and these are annotated with the @parallel annotation. We build the task graph over here. We have a big chunk of data. It's around 512 megabytes, a bit more probably, that we want to allocate through this array, float array. And then we have the task graph with these two tasks, and we transfer the data. And here is the first execution, but we can modify. We have the option, so every execution. We can also have the first execution for the array. And then we have the one task for the initialization, one task for the computation, and transfer data back. Through that, we create an execution plan, as we discussed, passing the snapshot of the task graph. So just to remember, nothing gets executed until this point. So this is just the definition. This is just to create an execution plan, and the application gets executed at this point. Let's go step by step and let's discuss one by one. So let's focus on the first one. I'm gonna comment all of it, and let's run step by step all different use cases and case scenarios. So what I'm gonna do is I'm gonna recompile the application and run it. To run, we have this command. And if I run, nothing should happen. We shouldn't see anything. I should now enable the, for example, the thread information, and that will print the device and the thread deployment, etc. Let's take a look. So if we do this, the application got executed on the NVIDIA RTX 3070, which is the NVIDIA GPU that I have on my system. And we see 2 times this information. Why? Because the information is printed per task in the task graph. So we have one task called S0T0 and the second task called S0T1. If we go here, we call it S0T0 and S0T1. We can change the name to say graph, and here we say init, and here we say compute. Maybe it's more accurate. So we need to recompile the application because we changed the source. So let's compile it again. And let's run it with the thread info. Now we see graph.init for the first task, graph.compute for the second task. What do we have here? We have the device in which the application was executed, and the number of threads that were deployed on that device. We're talking about millions of threads here, right? Okay, so this is because we just create the task graph, an execution plan, and execute. But we can do other things. For example, we can enable, let's do that, the profiler. And we have this mode called silent mode. And with the silent, we can query values after the execution. To query some values in the profiler, I have it here. Let's do this. So we can print the kernel time, meaning give me the time, the elapsed time, start to finish, just for the GPU kernel. We go this through an object called execution result from the execution plan, one is executed. And we get the profiler result, and we query the get device kernel time. And the time is given in nanoseconds. So let's do that. Let's recompile the application. And let's run it. So if we do that, we will see another, now we execute twice, right? Because the first time, let's go back, we execute with the default values, and then we execute again with the profiler on, in silent mode, but on. So if we do that, and we query the value, we see kernel in nanoseconds. This is the amount of nanoseconds to execute the GPU kernel. That's great. Let's do something perhaps more interesting. Well, before jumping to the device, let's now disable the profiler. So again, it's the same instance of the execution plan. We can enable, disable the profiler wherever we want. Let's do that. Let's, again, recompile the application again and run it. Now, let's go back. So first time we execute, we enable the profiler and we execute. We obtain the number of nanoseconds, and then we execute again without the profiler enabled, right? That's useful if you want to, for a while you want to check some values in the profiler and move on. You can query many things from here. You can query the total time. You can query, let me go back. The total time. You can query the kernel time as we show right now. You can query the compilation time, the data transfer time. This is the amount of time that took to move data back and forth. And you can specify, give me just the reading time, meaning from device to host, or the write time, meaning from the host, from the CPU, to the device, to the GPU. Give me the time for installation of the source of the binary in the GPU, etc., etc., etc. It's quite detailed. It might appear more calls in the future. So let's go back to our kernel time and let's continue with our example. Now let's do this. I want to change the device. And here I select device 0, 1. I know the values already, but let's take a look how I get those values. So I have Tornado here. If I do this command, if I run this command, I get 2 devices, right? Tornado does have devices, and I see the devices that are accessible from my instance of TornadoVM. And I see that the default device is the RTX 3070, the NVIDIA GPU, but I have another one. I have the Intel XD graphics. That's great. And how do I access with this to this GPU? Well, there are 2 values here: 0:0, 0:1. This is driver: device index. Driver, device index. So if I want to access to this one, I just put 0 and 1. I enable then the profiler, but in this case in the console mode. So I should see a JSON entry, let's say, as soon as I execute this. And I should see that the execution was migrated from this one, from the previous execution, from RTX 3070, from the previous execution to the new one. Let's see that. So let me recompile the application and let's run it. I'm gonna activate still the thread info to see all these changes happening. So let's run it. I'm gonna see even more and more things. Oh, the profiler in the console is working because I can see JSON entry here with very detailed. But let's see if we can, if the device was actually changed. So let's recap from the point that we print the values in the kernel. It's here. Okay, so that's the kernel time for the RTX 3070. Then I execute one more time without the profiler enabled, and then I change the device. And here I see Intel HD graphics 770. That's great. So we basically at runtime migrate the execution from one device to another. And because I enable the profiler in mode console on, as we can see here, I should see a JSON entry at the end of the execution. Basically, it's telling me all values that can be queried, like compilation time, bytecode generation, the CRAL compilation time. Tornado, remember, it uses CRAL for JIT compilation. The total time, all timers are in nanoseconds. The copy in time, the total kernel time, this is the accumulated time between all the tasks in the task graph, etc. And then you see an entry per task. This is where the names came handy, because if you want to know the actual compute time for one task, you can see from here, graph.compute, that's the offloaded part of this method over here. We call it compute for the second one, right? Graph.compute, and we can see the kernel time over here. This is the actual kernel time on the Intel integrated GPU. And how do we know it's the Intel integrated? Because the device selected is also here, right? That's great. And for the initialization, the kernel time is over here. The first time you run on a new device, Tornado will compile the code. Compile means, in this case, I'm using the OpenCL backend, which means that from Java bytecode down to OpenCL. That's great. Let's go a step further, and we can run with the warm-up. Now, as it is right now, this call will not do anything special because the code was already compiled for the last device we changed, right? But it's something that you could do. And we disable the profiler. So in this call, we should not see any JSON entry. Let's do that. So we got clean, Maven clean package again, and execute the code. Now we should see the last iteration after the JSON format. Now this is the execution without the profiler. Okay, so we can enable and disable the profiler on and off. If we want to, we can reset the environment. Just we say execution plan, free everything or device memory, reset the environment, because we're going to try something else. We're going to try this, the dynamic reconfiguration, as we described before. So if we do this, now we're interested to see the dynamic reconfiguration in action. So let's focus on this. What's going to happen is that Tornado will spawn a set of Java threads. Each Java thread will evaluate the execution for one target device. So it will launch one Java thread to run the evaluation on NVIDIA GPU. The Java thread doesn't run on the device though, it runs on the host, which is the Java platform. And it prepares the environment to run with the TornadoVM runtime on the target device. I hope that makes sense. And then the evaluation, in this case, I put it in parallel. We don't want, actually, we don't have access to the multi-core in this case, so it can be done in parallel. So if we do that, and we don't specify anything else, it's hard to see. So you have to trust me then. So if we compile, let's run it, and it's gonna get stuck for a while. And we see these weird names. This is because what the Tornado runtime does is that it rewrites the task graph, the original task graph, under the hood, creates a new execution plan, and it runs the new one for different targets, for different devices. And it has new names for it. It's just for evaluation under the hood. And then when finished the evaluation, it gives you an answer back. The answer is not printed because we need to specify a debug option. if we execute the same code and we call debug, then we should see more insights of what TornadoVM is doing with the dynamic reconfiguration. So remember, we are now evaluating this call over here. The printing, by the way, if you're curious, goes up before any of this evaluation, right? And in the performance mode, it runs the same task graph multiple times. So it runs the same execution plan multiple times. So hopefully it's finished. And we see that in debug mode, it gets something printed for debugging. It says, I evaluate the task graphs on different devices. I evaluate on GPU 1, sorry, in this case it's the NVIDIA one, the GPU 2, which is my Intel, and the Java version. And this is the amount of nanoseconds that took the evaluation in peak performance. And it says, I evaluate on all of them. To me, the best one is this one, right? And that's the integrated GPU. It's curious because we all will assume that it will be the powerful GPU that is the 3070. What's happening is that we might get that from the profiler though. The time to send data back and forth is expensive. So if the kernel is not that compute heavy and you have a lot of movement in data, you might get well with an integrated GPU. And that's what happened here. So my initial thought was that the 3070 was the best option, but Tornado says, no, it's the second GPU. And the second time we run the same application without telling anything else, the execution should stick with the choice that Tornado said, which is integrated GPU. Let's see that. So if I compile the application and run again, it's now evaluating. This is a heavy process though, because it's evaluation. It doesn't speculate though. It actually evaluates on all platforms and gives you the best answer based on that policy, which is what we want though, but there are other ways perhaps to achieve this as well. So we wait until this is finished, and then after the evaluation, we execute one more time. And remember, I execute with thread info enabled, and I want to see the option that took. It says, I choose the device 1, so I'm gonna run on device 1. That's great, right? So that's what the dynamic reconfiguration does. All right, that was fun, right? So I will put a link in the description down below with the examples that we saw today. And with that, I conclude this video. I'm preparing new tutorials about how to port applications, how to analyze performance, etc. So if this is something that you are interested in, just stay tuned. Happy coding and see you soon.